Right, everybody, welcome to our third STARS PD. This one's going to be on star clusters, and we have Dr. Sven Buda, who's one of the academics up here on Mount Stromlo, who's going to be helping me with the trickier sciencey bits. We've spent a bit of time going over the talk so far, so I'll do a little bit, Sven will do a bit, I'll do a bit, and then we'll take some questions at the end. But as we've said before, please put your hand up, call out at any point during it. We're more than happy to take questions and comments as we go, particularly as this one is a bit heavier in some of the science than the other two have been. And so if you find that we are moving a little bit too fast, please give a hoy and we'll pull it back and start again. So, star clusters. The first sort of question is, why would we do star clusters? And really, it's because they're the things that you can see with the telescopes that we've sent out to everybody. Ptolemy was the first person to name one in 150 AD, and is now called Omega Centauri, but it was seen with the naked eye as a single star. You can see with star clusters, they are absolutely beautiful. The one on the left there is the jewel box, and the one there on the right is 47 Tuc. Now, the interesting thing with these is that these pictures are taken with professional telescopes, and so we can see a bit more detail, but they are very, very different from one another. We'll start with this one. So the jewel box is an open cluster. So it has tens to hundreds of stars. They're only a few million years old, and they're located in the disk of our galaxy. 47 Tuc, though, is what we call a globular cluster, and it has tens of thousands to even millions of stars, this style of cluster. These tend to be a few billion years old, remembering that the universe is only 13.8, give or take, billion years old. And they tend to be located in the bulge meaning this bit, or the halo, meaning this larger area here of our galaxy. And so if we make a comparison, they're quite obviously different but similar. Okay, so we've got our miniature bunchings of stars. Now, what is a star? So we're all familiar with The Lion King, I'm assuming. So Pumbaa from The Lion King got it right when he said, "I always thought stars were balls of gas burning millions of miles away." And I think Timon says something about everything's gas with you. But not all stars are actually the same. And so if we change the mass of a star, the mass is the most important of the intrinsic properties of a star. And just to clarify so that everybody's on the same page, when we're talking about mass, we're talking about the amount of stuff. So on a good day, I have about 60-something kilos of stuff. Our star has 2 × 10⁻30 kilograms of stuff. And my mass and our sun's mass would be the same regardless of where it was. So if I was up on the moon or floating about in space, my mass would remain the same, just so we're clear on what we mean by mass. And so if we're talking about a big ball of gas, then the more mass there is, the more gravity there's going to be to pull and compress and squeeze that star harder, and so it's going to produce more heat. And the temperature of a star is what we define as its color. And so red stars are cooler and blue stars are hotter. So for instance, this is the spectrum of our sun. You may have seen this sort of diagram before. We have the wavelength here. We're going to do it in nanometers. That's the general wavelength measurement. What do you call them? Unit of measurement that astronomers use is nanometers. We've got our visible bit here, so we just generally think of the optical bits that we can see with our eyes as being around 400 to around 600, 650. And the peak for our of the strongest of those wavelengths for our star is about here. If we then place our star on a graph showing a couple of others, we've got red star over here, 3000 K, K meaning Kelvin. So it's only 273 degrees different from the Celsius scale. So to all intents and purposes, 300 degrees. It's cooler and it's not giving off as much light as our star, which is about a 5000 K. And then blue stars over here are nice and hot at 8000. So we've got the mass of the star then leading to information about the amount and the color of the light. And then we've also then got that defining the life cycle. And so the big stars live fast and die young, and they burn up the fuel very quickly. The last property I'm going to talk about before handing over to Sven is something called magnitude. And there are two magnitudes. There's the apparent magnitude, which is how bright a star is in the sky. And this is great if you're going to be cataloguing the objects that you want to look at through a telescope. So only the ones that are bright enough can be seen. But of course, that means that a star that is very bright but a long way away versus a star that's dimmer but closer to you can appear to be the same apparent magnitude. And so they're not really useful for doing any physics on if that's the scale that you use. And so astronomers have come up with this idea of the absolute magnitude. And so if you could theoretically put all of the stars at the same distance away from us, so in this case it's 32.6 light years away, then we can then make comparisons when we're comparing apples with apples. Right. I will stop there and hand over to Sven.
All right, thanks, Lara. Let's see if the technology is also working on my end of the screen. I hope you can see that. So what I will try to explain to you is how you can basically sort stars based on their color and how bright they are. And we're going to do that with just this big patch of the sky on the left-hand side. I'm going to already zoom into a region where I know that there's an open cluster. So I know that the stars at the top of this picture have actually been born together. They're at the same distance. And what we're now going to try to do is from this very low quality picture, let's assume that we have observed 400 stars and we have actually observed them and their colors. So the great thing that we can do with an open cluster like this one is called Messier 67. We can actually now try to sort them. And let's first do that by their color. So now the stars are moving left and right, depending on if they look blue or red. And you see that, well, there's a few red ones, a few blue ones, a lot of stuff in between, and they have all different kinds of coordinates. But if we also sort them by how bright they are, actually, then we go from the faintest at the bottom to the brightest at the top. And this is one of these magical moments for an astronomer to see this for a cluster. This is a sequence of the different stars that we have. And there's a lot of great things that we can see here because this sequence is actually estimated based on the mass that stars have. When stars have very low mass, they basically, as Lara said, like the bigger they are, the faster they burn through the fuel. These very low mass stars, they take a huge amount of time before they burn through their fuel. So for example, the sun will actually stay on this, what is called the main sequence here, for 10 billion years. So the sun currently is 4.5 billion years old. So it will take another 5 billion years before the sun actually has started to run out of fuel. And what then happens is this intricate play of contraction and expansion, where some of the parts of a star will actually start to expand. And when stars expand, they become brighter, so the luminosity increases, so they go up. But at the same point, that also includes that, for example, the outer layers of a star become cooler. So what they do is they walk up this interesting walk towards the so-called red giant branch. And it's called that, classic astronomer slang, because these stars are having really large radii and they are typically redder. So if you look at a star in the sky that appears redder, you can automatically infer that it's typically a cooler star. And then there's some interesting stuff that happens. The fuel that stars burn typically is hydrogen in the cores. There's such a big temperature that you can actually fuse hydrogen to create helium. And when you keep doing that and you basically burn this fuel away, something that will happen is that the core contracts even more, and more contraction always means more temperatures. And more temperature means that at some point you actually can start to also burn helium. And what happens then is that you actually have this kind of ignition moment where you start to burn helium. And this will basically place these stars on one very specific part, which is called the red clump, because it's similar to a second main sequence, where in the first main sequence, stars burn hydrogen. In the second main sequence, what we call red clump, stars burn their helium. And so you have these very interesting moments in the lifetime of stars, or in this sequence of stars with the same age, that really allow us to do a lot of great things, like not only estimating the temperatures, but also if we have this sequence for different stars, we can use that to estimate distances, because the only difference between the absolute and the apparent brightness of these stars is the distance. And so there's a lot of great things that we can learn from that, including the estimation of ages. And that's something that you can play around with if you want. So one of the resources that we'll share with you at the end is this interesting link here, where you can basically assume or play around with different masses of stars and see how they evolve in their radius, in their temperature, and other properties. But before I hand it back to you, Lara, one thing I want to point out is hundreds of years ago, people already started doing that. They basically created these interesting diagrams with, at the time, 150 stars. So this is how the whole game started. But now we have actually satellites observing the distances of stars for us and the colors and magnitudes, and we can put billions of stars into these diagrams. So this is something that I work now with in my everyday life, which was a revolution 5 years ago when we had this first data, that we now actually know the distances to like a billion stars. That is kind of unheard of. And I'm going to give it back to you now, Lara.
So I might just do a little bit on how to locate some clusters with your telescopes. So again, can I do, is that going to work? Yes? Very good. Okay. So we'll start with the Pleiades. So the Pleiades is known as the Seven Sisters. It's an open cluster with about 100 stars. And so the way to start that one would be to find Orion the Hunter. I'm assuming people are relatively familiar with Orion, yeah? So I always find it easy to find the belt and the sword and the feet and the shoulders. And I know there are other bits of it, but they're the ones that to me stand out the most boldly in the sky. So if you run a line through the belt, and then I shall just, sorry, I'll just admit somebody there. And then we head off to the next brightest star, which is almost in the same line, so Aldebaran star, and then a little kink off to the side, and there's the Pleiades. So that one is a relatively easy one. I find it interesting that it's about 100 million years old, which makes it about the same time as the time of my favorite dinosaurs. So I really like Ankylosaurus and Pachycephalosaurus because they were in childhood books of mine. Anyway. Jewel box. This is the one we talked about earlier. So it's about 14 million years old. And what we need to do here is find the Southern Cross. And there it is. And then it's just there. The jewel box is right near the left-hand side of the cross, if we think of this one as being the top. And it's in the scheme of things very young, only 14 million years old. 47 Tuck is a favorite of some of the academics up here on the mountain. It's 12 billion years old, give or take. Again, remembering the universe is only about 13.8 billion years old. So to find it, find the pointers. We've got pointers here, find the brightest, draw a line down from there through the Small Magellanic Cloud, and there you will find 47 Tuck along that line there. So it's all about finding things that are familiar and drawing lines and then veering off just a little bit to the sides. And Omega Cen, that Sven may talk about in a little bit, is one that I added at the last minute today, but this one again, we find the Southern Cross, and here it is. And if we imagine again, this is the top, I always think of that as the top. And then we shift off in this direction to a patch that doesn't have as many bright stars. You find a fuzzy patch that's over here, and this here will be Omega Centauri. And I shall now hand back to Sven to do some more tricky science.
Thanks, Lara. Yeah, what I'm going to try to tell you a bit more about is why we actually care about this. So one of the questions that I have, and I hope that you have a similar question when you look up at the night sky, is how did all of this form, right? How did the Milky Way form? how did the constellations that we typically see, the Southern Cross, or if you have heard about the Aboriginal astronomers, they actually use all of these dusty regions for their constellations, like the emu in the sky. How do all of this form? Well, if we look at this picture of these billions of stars, so this is actually not a picture of like taken of the night sky, but that's like basically 1.5 billion pictures taken and combined, right? One of the things that we can see is this kind of milky band. So this is what you see on the night sky, of course. We've understood that this is coming from the disk of our Milky Way, or the galactic plane, as we call it. And that's because we have a lot of dust that is obscuring regions where we have tons, and tons here means hundreds of billions of stars that are actually in this band. We also have this bulge region in the middle where we have a lot of stars condensed in the center of the galaxy. And we have this halo. And this is where we find our open clusters. As Lara said, they're closer to the plane, like the Pleiades, or other clusters like the globular clusters, the more heavy or like more numerous clusters with more stars. They're spread all over the place. And of course, we're not going to talk about external galaxies today, but what is really interesting from this picture is already just by looking at this Milky Band, we understand that the Milky Way is a disk galaxy with a bulge and a lot of substructures like star clusters. And one of the things that people have done more than 50 years ago is they actually started counting stars. And if you do this counting as a function of going away from the plane of the galaxy, basically what you have to do is you have to not only assume one population of stars in the disk that would allow you to just fit a line to what you see here as the number counts, but you actually have two different populations. And astronomers have been very clever in naming these populations. One, because it's closer to the plane, is called the thin disk, and the other one, you might have guessed it, is the thick disk. But one of the big questions that we have not really understood is why we have these two populations. So we've done a lot of observations and we have a lot of ideas. And one of the ideas that I'm currently investigating is that possibly we had a collision of the Milky Way, the young Milky Way in its childhood, with other galaxies. And just to give you an idea of how this could look like, this is what our current best simulations of Milky Way analogs of like basically made up Milky Ways could look like. And you have a lot of things going on. There's a lot of collisions, smaller galaxies, globular clusters, everything can possibly come together, sometimes a big galaxy, and you see that does a lot of things to our potential Milky Way. Now, in simulations, we of course know exactly what's going on. So if you, for example, would like to color code the Milky Way and another galaxy that's going to collide with it in a simulation, like this one here from Helmut Koppelmann, you can easily do that as white and yellow. Now, in reality, when this merger happens, everything is gonna mix. And if you take pictures, you cannot really tell apart stars based on this color, because the color, as we learned before, is correlated to the temperature. So we can't use this color. So one of the things that we can go back to is we can actually not only take the pictures of the stars and look at the color, but we can actually use the prism or some other optical instrument to split the light in its constituent wavelength. And one of the cool things that you can see here is if we look, for example, on the left at hot stars and on the right at cool stars, there's a lot of different things going on, a lot of features. And we have understood by observations from Earth that some of these elements, or some of these features are caused by elements that are actually absorbing the starlight at the outer layers of stars, so that the light with this wavelength is actually not reaching us anymore. So hydrogen is, for example, one of the most numerous elements in stars that's doing a lot of absorption. But you also have, for example, sodium, you have iron, you have molecules sometimes, a lot of different things that can go on. And you may have seen the periodic table before, but possibly not this version. So this is the version of how I think about the periodic table, because different elements have different wavelengths in which they either emit light when you heat them or absorb light in the atmospheres of stars. And we can do a lot of great things. And we can use these spectra. So this is a spectrum of the sun. We can use them as barcodes, right? You see all of these different features and we know exactly which elements they belong to. So just by measuring the absorption strength of these lines, we can do a lot of different things and really understand how different elements of the periodic table are created. And we've come to understand that a lot of these different tables, a lot of these different elements are created through different processes. So for example, exploding white dwarfs, which are like really condensed small objects that if they're basically overeating from a companion star, they basically just explode. You can also imagine that exploding massive stars, when they die at the end of their lifetime, they also eject a lot of material, and we can form new stars from that. Or also we can just have all of these elements deposited, for example, in the sun or in planets like our Earth. So a lot of the elements that you see here are actually made in stars. So like Carl Sagan said, we're made of star stuff is really like true. And you can even see in this table where these different elements come from. But I just want to quickly walk you through how this works, because I'm a spectroscopist, so this is my my daily exercise, looking at these spectra. So this is the absorption features that you can see in the sun. And I have to warn you, I'm typically not working in nanometers. I'm dividing nanometers by 10 and call it angstrom with a fancy Swedish O that you see here. It's basically around 480 nanometers. And you see a lot of absorption features going on. And if you would, for example, increase the amount of elements in an atmosphere of a star, you would, of course, be able to absorb more light. If you would decrease the amount by a factor of 10 or even by a factor of 100, you already start to see that we have less elements that can absorb. And the most extreme star that we have found so far today has like 1 millionth of the heavy elements, like everything from lithium onwards, than the sun. And the only absorption feature that you see here is actually hydrogen, because there's a lot of hydrogen in stars and the universe in general. And so one of the things that I'm actually trying to figure out is to find survivors of these galactic collisions that I talked about before. Because when a collision happens, we of course lose all of this information of how stars move around, because there's a lot of mixing going on. But one of the great things about spectroscopy and about the chemistry of stars is that once a star is born, it's locking its material in its atmosphere and it doesn't change. So we can really use these stellar spectra as barcodes, or you can also imagine it like a chemical fingerprint. They don't change. It's like DNA. They really don't change that much. So we can really use them to find stars that have been born together, or even more interesting, to find stars that have not been born in the Milky Way. And just by looking at different elements, so at the top, you see all of these different labels telling you which elements they are. And similar to you, possibly not knowing what La means, I also have to look at my personal periodic table. That's why I have it on my mug, to figure out that La means lanthanum. And we can figure out if we just can take different combinations of these elements and find stars that are born in the Milky Way or not. And so this is, for example, one of these combinations of looking at the ratio of sodium, Na, and iron, Fe, on the x-axis, and magnesium and manganese, Mg to Mn, on the y. And basically what you can see is two different populations here. And I hope you all had lunch. So one of the things that we can do is we can look at these scrambled eggs in yellow. These are actually stars that are not born in the Milky Way. And they're very different from the avocado, which you see on the right. Those are stars that are born in the Milky Way. And so this is some of the things that we're actually doing observations both at ANU, but also at Siding Spring Observatory, like 8 hours north from Canberra, to really observe more of these stars and figure out how stars and in the Milky Way basically assembled. All right, I have one thing that is completely out of order, but I thought that might be interesting for you. Lara told you before that we can use these stars, for example, to figure out ages or sequences here. One of these interesting clusters that Lara showed you before is Omega Centauri. Now, one of the things that we expect for clusters, if they're simple populations, is that we only have one sequence. So one of the interesting things that is still puzzling astronomers today, and we actually do a lot of research into this, is that for Omega Centauri, we don't have one sequence as we saw it, for example, for M67, but we have several. And there's a lot of different ideas out there why that is. But one of these interesting ideas is that we actually have different populations of stars in one cluster. So you basically have some very old ones and some even older stars. Or you can also imagine that you have some really metal poor or some really element poor stars that only have hydrogen and helium, and some that have more of the heavier elements. And that will basically shift how you evolve in this diagram. And I think one of the things that I always like to think about for star clusters is you can imagine that open clusters are not a lot of stars in them. They're very young, so you can imagine them as toddler groups. And actually with the Seven Sisters, that's like, what a nice analogy. Whereas star clusters, like globular clusters, are more like the retirement homes. We have a lot of different stars in there. They're typically quite old, and they have stayed there for quite some time and will continue to stay there for quite some time. So if you think about open and globular clusters, maybe that can be like a quite nice way to remember the ages. All right, back to you, Lara. You're still muted?
So before I share my last slide, which is just a couple of suggestions of some resources you might like. Does anybody have any questions? No? Well, stunned into... No? All good? All right, in that case, I'll just show the last one, which really is just some resources that I'd recommend that you're going to have a look at. So there is that, there's our website that has the resources for the classroom, the teacher resources. I think I showed them last time. There's also a nice resource at the University of Melbourne on Indigenous astronomy. If you haven't seen that one, there's some more technical information on astrophysics on the old CSIRO ATNF website. Stellarium, if you've not come across it, I use the web-based one to take screenshots to make those diagrams to show how to find things. Sven has it on his phone. And as a professional astronomer, he isn't fantastic at navigating the night sky. I've got permission to say that, so he has it on his phone. Yes, thank you. And there's that link to that star in a box, which is a sort of JavaScript type interactive, and you can fiddle around. You can have the simple version or the more complicated version, and it's all just web-based. It's quite interesting. And I'll also acknowledge Wei Shen O, whose video on the ANU TV channel I perused before preparing this talk. And there's a link to that, and he does a very, very good job if you're interested in looking at his stuff.